Do you see the PowerPoint presentation, all of you? Are you able to? Yes. Okay, good. So then let's get started. It's about 5 o'clock. I would like to go over some important concepts from chapter 1 and chapter 2. Chapter 1 is just an introduction to geology and some important concepts, and the chapter 2 is about minerals. And next week, the topic will be the plate tectonics. No, that's not plate tectonics. It's igneous rocks. So you are prepared for the upcoming assignments. Then, do you have any questions at the moment? Anything about the course? Okay. So then I don't see any questions from anyone. So I'm gonna get started with the chapter 1. Are you able to see the first slide of the PowerPoint presentation? Okay. All right. So then let's move to the first slide of the second slide, the information slide on the PowerPoint presentation, and we see some figures here. This slide is trying to illustrate the benefits of geological investigations. So geology is a science, logos science, and geo is earth. So it's basically about the earth, science that explores, tries to understand some natural phenomena about our planet Earth. Now, why do we need to do investigations, scientific investigations of our Earth systems? Well, and some are shown here. And look at this first figure to the left. We see a pencil there in that figure, and then a list of things are commodities that are required to produce a pencil. And look at this, we need zinc and copper, for that holder that holds the eraser. And then, of course, the rubber is a petroleum product which comes from the earth. The machines which polish and cut the wood require iron, and the pencil is looking yellow because of the paint. And the pencil lead itself is actually not lead, made of lead. It's made of a mineral called graphite, and there is a good amount of clay in the pencil lead. Higher the clay's amount, harder the lead becomes. So all these materials are not produced in a lab or in a factory setting. You really need a rock with pertinent minerals. And another problem is there is no copper hill or a zinc hill or a graphite hill. One needs to search for these commodities. So that's where the geoscience comes in. We have scientific principles that help us find these commodities, and so we can go about our industrial activity with all the raw materials supplied. Now, sure, geology helps us to find materials. How about the phenomena like volcanic eruptions? Look at the figure there, which shows if a huge volcanic explosion occurs, what ensues right after it. And you can see a large cloud of ash. And this ash cloud can fall back and flow at more than 100 miles per hour speed, incinerating anything in its path. So we should be able to predict when a particular volcano is going to erupt. Likewise, the bottom two figures are about tsunami events. The bottom, the figure with the map, part of the world map, is about an event that occurred in 2004 You perhaps heard about this. There was a tsunami event in the Indian Ocean, which killed more than 180,000 people in different countries. So it was a big event, and it was caused by an earthquake. So then, these are all natural hazards. Is there any way to predict? Um, sure, that's where the geoscience comes in. Likewise, if we have environmental pollution because of human activity or due to any natural phenomenon, we should be able to recognize it and manage it because we live in that environment. So we don't want our living environments get contaminated by them. So here we go. So these are all some benefits of geological investigations. Um, so then geoscience is a very beneficial activity, right, for our society. So then, what is this geoscience about? What does one learn when that person begins to study this discipline, this branch of physical science called as geology? Well, obviously, it's about Earth. Now, what is Earth? Earth includes the planet Earth, the rocks, minerals, not just planet Earth. It's also the water, right on at the surface, and it's also about the atmosphere made of gases, and we are part of it. We are part of the Earth, so including us, the biosphere, like plants and animals. These are all included in these are all part of our Earth. So we can look at Earth as four major subsystems: geosphere, rocks and minerals; hydrosphere, water; atmosphere, gases; and biosphere. We are part of this biosphere with plants and animals. And if you look at the figure on the slide to the left, it is showing the planet Earth. It is also showing some details about Earth's internal organization, meaning the Earth materials that make the geosphere are not uniform throughout. That is, from the surface of the Earth to the center of the Earth, these materials are not uniform throughout. They somehow they appeared to have gotten segregated into, say, core at the center, mantle outside the core, and then near the surface there is crust. So crust, mantle, core, going from surface to the center. Also, it looks like there are two areas in the core: outer core, which is a liquid; inner core, which is a solid. In addition, we also see some details shown at the crustal depths. If you see that small, zoomed in area, you see terms there like crust, uppermost mantle, asthenosphere. Let me see if I can. Okay, so I'm talking about this part here, right? You can see in that area, you can see crust, uppermost mantle, asthenosphere, and we also see lithosphere here. So that's another division. So then when the crust moves, it takes with it the uppermost part of the mantle. So we had to create a term that to answer that. So we call that as a lithosphere. And right below lithosphere, we have some what we think it is a warm, hot area inside the Earth. Semi-molten rock is ready to melt, not molten completely, ready to melt. So we have lithosphere made of crust and uppermost mantle, right below it is the asthenosphere. And right below asthenosphere is the rest of the mantle. And then below the mantle, we have a liquid outer core. And then inside, at the center, we have a solid inner core. This seems to be the internal organization of our planet Earth. Um, any questions so far about the internal organization of the Earth? Okay, so it seems there are no questions. Now, it also shows here engines. So we have good reasons to believe that Earth's systems are mobilized or affected by heat engines, H-E-A-T, heat engines. So what is the function of engines? One of the functions is to move material. So the materials of the Earth are being moved by these ever active engines. And heat is the main source of energy for these engines. There is an engine inside the Earth, there is one outside the Earth. We know that when a solid absorbs heat, it's heated, it becomes less dense. So there is a possibility that it rises. If it loses heat, it becomes again dense material, so it sinks. So the engine Earth has inside of it seems to be heating the rock materials inside the Earth, making them to rise towards the surface, like what we see in a lava lamp. And once these materials move away from this heat source, they cool down and they sink back. So we have good reasons to believe that in the mantle, we have these circulations happening. Now, how about outside the Earth? Outside the Earth, atmosphere is getting heated on everyday by the sun. So this heat, what does it do to the gases? Well, again, they warm up, they become less dense, they rise, they cool down, make clouds, it rains, and then once the gases cool down, they sink back to the Earth's surface. So we have reasons to believe that these engines, one inside the Earth, one outside the Earth, mobilize Earth materials. So that's basically is about this slide. Now on the next slide, we'll see the effects of these engines. First, about the engine that is inside the Earth. What does it do to the Earth materials inside the Earth? It makes them move, circulate, and transfer the heat energy to this right from the interior to the surface area. And guess what happens as a result? The Earth's outermost lithosphere, we just talked about it, or the crust, has a tendency to break as a result of this heat energy that is transferred by the heat engine from interior of the Earth to the surface. And you perhaps heard about shifting plates. So how can a large slab of rock can shift? Well, the internal heat engine can do that. Just like what happens to the lid if you place it on the top of a container with a boiling water. We know that it jumps. So that's how the crust tries to jump, but it can't. Instead, it breaks. And as a result, crust is not a continuous layer anymore. It is now broken down into fragments. So these fragments always in a continuous motion, making earthquakes, volcanic eruptions, and all such related phenomena. And now, what does the external heat engine do? We know that atmospheric gases circulate, as a result of this engine's work. And what does this engine do? Well, one main result of this engine is rainfall or snowfall, depending on which geographic location we're talking about. Now, The rainfall, once it hits the ground, it has two choices. Well, there is one more minor choice. The first choice, it can flow on the Earth's surface and then maybe like make streams, or it can go underground and become groundwater. Now, what can river water do to the rocks? Well, you perhaps heard about this. Weathering can happen as a result of water's action on rocks. Basically, what it means is that rock breaks down, right? Breaking up of rock physically and chemically at the surface of the earth due to the action of elements. That's weathering. What is the result of such a process? Rock breaks down, right? Breaks down into fragments. Once the rock breaks down into fragments, rivers can move these fragments. So, and what is the ultimate fit of all these moving fragments that are being moved by air, water, and maybe glaciers? Their final destination is the ocean. Like, look at around us in the valley, it's all sediment around us. Where did it come from? Well, that came from somewhere else. Majority of that was brought to this location by streams. Just like there is a hill at Rio Grande City area, and what you see there is volcanic ash. And how did the volcanic ash get here? There is no volcano here. Well, West Texas had a volcano, and that ash fell into a river, and that river brought that ash to our location and deposited it there. So transportation. So weathering, erosion, transportation, and then eventually all this is getting into the sea. And guess what happens to it once it gets to the sea? It turns into a rock. You see, the mountain loses the rock, whereas the sea gets it and turns that into another different type of rock. So now the question is, what happens at the mountain site? If it loses the rock, does it affect it any manner? And we know that it does. As this figure indicates, figure A shows a mountain, also a sea, and figure B shows the mountain got weathered away, lowered, and then sediment got to the sea, and that is the yellow layer in the sea. That is right here, right? This yellow layer. Let's see if I can get a pencil, right? That's a yellow layer, and that's a sediment layer right there, right? And what happened here? The mountain lost some of the rocks. So see these arrows here. So what does it indicate? It indicates that the rock here gets uplifted. Why? Because mountain lost some rock due to the weathering. As a result, the entire area is uplifted, and that we call as isostasy. So look at the work of these two engines. Internal engine moves rock from deep earth to the surface, thereby transferring the heat energy, and shifts plates, makes volcanoes, makes magma, rocks, earthquakes, makes mountains. Whereas the external heat engine weathers the rock, removes the material, and uplifts the crust. So these are large-scale movements, and they are the products of these Earth's engines. And all these changes require a lot of time. And Earth, the age of the Earth was found out to be about 4,550 millions of years. So that's a very long time. And all through these years, Earth had been very dynamic. These internal and external heat engines, they have been moving the materials, causing earthquakes, volcanic eruptions, plate shifts, rise of land, weathering of rocks, sediment formation in the sea, and so on, right? So that's the basic framework of geologic processes, right? And you'll see that in the following chapters, we actually zoom in. Like so far, we talked about the Earth as a planet, at a planetary scale. And the chapters during the semester will allow you to go close to, observe the Earth at a small scale, right? Um, Scenario. Do you have any questions about this chapter? Introduction to Geology. Anyone? Questions? All right. So then, what I will do is, I don't see any questions. No one has posted any questions. So what I will do is, I will go to the next chapter. Which is going to be about minerals. So I'll briefly go over some important concepts from this chapter, right? The question is, what are minerals? Can someone type an example for mineral? Any example that you know about? Anyone? Do you know any mineral? Well, diamond. That's a good example, Erica. Diamond is a mineral. Now, what are some characteristics of mineral? For example, a diamond. Is a diamond solid, liquid, gas? Which one? It's a solid, right? We all know that. Now, what are all natural diamonds made of? Well, we know that they all are made of carbon. So there you go. Those are first two important characteristics of minerals. Minerals are solid materials, and they have consistent chemical properties like composition. All the natural diamonds are made of one element, carbon. So one way to distinguish a true diamond from others, if they are naturally formed, is checking its composition. So all diamonds are made of carbon. In addition, all minerals have definite internal structure. So inside a diamond, for example, all carbon atoms are arranged in a particular definite arrangement, and this arrangement extends in all the three dimensions. So diamonds are solid materials. They have a definite chemical composition. They have an orderly internal structure, and they're naturally formed. So let's see. What we see here is in the leftmost figure, we see a rock. A rock is usually made of more than one mineral, and each mineral is made of either one or more than one element. So right here we see silicon and oxygen. So these are elements. So this structure seems to be made of these two elements, silicon and oxygen. So then what is the relation between the chemical elements and minerals? Minerals are chemical compounds. So when atoms of elements chemically bond, the result is a mineral. And what do we call the chemical bonding of elements? It's a chemical reaction. So chemical reactions that happen in nature produce minerals. So minerals are basically chemical compounds inside which atoms are bonded to one another, or atoms of one element are bonded to one another, or atoms of one or more elements. Like for example, on this figure, you see a set of atoms shown right there. All atoms have nucleus at the center and electrons surrounding the nucleus. like is shown right here, right? Nucleus has protons and neutrons, and these blue dashes are electrons. Electrons revolve around the nucleus in definite orbits called as electron shells. Right here we see sodium, what we call as ion shown. Why am I calling it as ion? Because I see plus charge here, right? Likewise, I see chlorine ion right here. Why am I calling that as chlorine ion? Because I see a negative charge. Now, why do we see these charges, Na plus, sodium plus, and chlorine minus, Cl minus? That's because if you observe the color of these electrons, um, you see one of the sodium electron was transferred to the into chlorine's atom, right? So it was one electron from sodium atom was removed and was added to the chlorine's outermost electron shell. So that's what happens during chemical reaction if sodium and chlorine are involved. Sodium loses one electron, it doesn't mind because that makes it stable, and chlorine receives it. Sodium gives, chlorine receives. That's the chemical reaction. One way of atoms, elements can, react is electrons getting transferred from one atom to another. And as a result, the sodium atoms develop a net charge. Chlorine atoms develop a net charge, and they develop attraction for one another, and they cling, atoms of sodium and chlorine with those net charges called as ions, they cling and make a compound, sodium chloride, which is our table salt. So that's how minerals form when atoms chemically bond, either this way or there are other options. Once they chemically bond, they build the basic structure and turn into minerals. So then elements, what kind of elements are present in our Earth's crust that chemically bond and make minerals? Well, although we know more than 100 elements, only 8 of them make more than, you can see more than 90%, right? Almost 99% of our Earth's crust. Topmost is oxygen in this list, and magnesium is the least abundant. Oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. These are the most abundant elements. You can see oxygen and silicon are the most abundant compared to all other elements. Oxygen and silicon are the elements of our Earth's crust. And what we see right here are the structures these two elements make, silicon and oxygen make via chemical bonding, that are present inside minerals. As you can see, 1 silicon, 4 oxygen atoms make this structure. And these structures have a tendency to chain up, just like people holding hand to hand, right? They make a chain, a line of, right? Standing side to side, if they hold hands, they make a big long chain. So these structures can chain up like that, like what you see right here. But there are other ways for them to chain up. And what is the result? Result is silicate minerals. So if these structures make minerals, we call them as silicate minerals. We see some examples for silicate minerals right here. These are all silicate minerals. What does it mean? It means they have that chained up structures inside them. These here are non-silicate minerals. What does it mean? They do not contain those chained up structures. Instead of them, they have other elements inside them. Now the question is, which are more abundant in our crust? Silicate minerals are the most abundant type of minerals in our crust. And as a matter of fact, this is a feldspar mineral. These are the most abundant minerals present in our crust. Now, All minerals have their own set of physical properties. What are physical properties? Why are they useful? For one thing, they help us to understand the mineral we are looking at, and many times one will be able to identify it just by looking, observing the mineral properties, and making a note of them, and finding a way to name them. Physical properties are like fingerprints of human beings. Fingerprints can help in identifying human beings. Physical properties can help in identifying minerals. Now, what are physical properties, and what do we do with them? Well, I listed some important physical properties here on this slide. Luster, color, streak, hardness, cleavage, specific gravity. Um, some important types of physical properties. We'll just go over them. Luster. Luster is the way mineral reflects light. The way mineral reflects light. Just like, for example, let's say you're trying to read a credit card. You know how you're going to look at the credit card if you want to read the number out of it. You really will tilt it until you see the shine on the credit card, so you can read the number. That's how one can observe the shine on minerals. And we describe the way the minerals shines, or the way mineral reflects light, as luster. Two main categories of luster: metallic, non-metallic. Can someone tell me which is the mineral out of these two that has a non-metallic luster? Let's see. Is it the one which I circled, or the one that I didn't? Which one is the mineral with non-metallic luster? Can someone type? The one to the left or the one to the right? Yeah, that's correct. Yes, and yeah, that's right. And the one to the right, you can see it is reflecting light like a metallic luster, like a metal, right? So that's a metallic luster. Color is the simplest property. You look at the visible hue and then describe. You can see the color of this mineral, the one I circled, it's almost colorless because light is able to pass through it. Maybe someone can describe it as white or colorless. Can someone type the color of the mineral to the right that is shining like a metal? How do you describe the color of it? Like brass yellow, right? That's how you describe the color. How about the streak? Streak is minerals powder. Streak is the color of minerals powder. Like for example, the one to the left is almost colorless. Guess what its powder's color is going to be? It's going to be white. And it's not going to be colorless powder. It's going to be white. And guess what the color of this mineral is going to be? It's going to be gray, dark gray. Not going to be brassy yellow, right? Brass yellow. It's going to be dark gray. So there, streak is the color of powder of its mineral. That is color of minerals powder, right? So then streak of the mineral can be a different color compared to the color of the mineral itself. Now, what is hardness? Hardness is a measure of minerals' resistance to abrasion. And we can rank minerals based on their ability to withstand abrasion. So when we say abrasion, what we mean is let's see, what is a good, when do we actually abrade some material? Now, for example, if there is when a car bumps into something, right? Or a toy car bumps into the wall, for example, right? Then the tie coil will abrade the gypsum board. Because gypsum board is soft, it gets abraded, right? So abrasion. Um, so using friction, we can try to abrade materials one with the other. So uh, higher the power of the mineral to withstand abrasion, harder the mineral is. Right here to the left, we have a figure that ranks minerals um, based on their ability to withstand abrasion. You can see diamond is near the top. Mineral talc is near the bottom of this scale. So talc is the softest mineral, diamond is the hardest mineral. In between we have other minerals. So these are standards. These minerals, talc, gypsum, calcite, and so on, they are standards for these hardness values. So that's 1 through 10. 1 being softest, 10 being hardest. So diamond can abrade all these minerals. Corundum can abrade all these remaining 8 minerals, but it cannot abrade diamond, and so on, right? So we determine the hardness of minerals using scratch test. We may use tools like fingernail, human fingernail, window glass, copper penny. So using these tools, we can estimate the hardness of minerals. Cleavage. Cleavage is the ability of minerals to break in predictable manner along flat, smooth planes. For example, if I break this mineral right here, it may be possible for me to get similar shaped, rectangle shaped fragments from it. If I break this mineral, it will never break in a predictable manner. The one to the left breaks in a predictable manner with flat, smooth planes. The one to the right with metallic luster will never do that. So I can conclude that cleavage is present in the mineral to the left and it is absent in the mineral to the right. So cleavage is the way mineral shows a tendency to break in a predictable manner. And like is shown right here, this mineral is shown breaking in a predictable manner because I can see it broke down into smaller fragments with similar shape. And guess how many directions, along how many directions this mineral tends to break? It tends to break along 3 directions, like what is shown right here. 3 directions, 1, 2, okay, 1, 2, 3 directions. How about this mineral? It has only 1 direction. How about this mineral? It has 1, 2, 3. But what is the difference between these two? It is the angle, right? Here, the angle between the directions is 90 degrees. Here, it is not. So that's cleavage, a tendency of minerals to break along predictable planes. Now, what determines the hardness and cleavage? It is the presence of weak bonds in a mineral. Weaker the bonding is, easier for them to break, and so the mineral tends to be softer, or it will tend to break along some predictable planes. So chemical bonding determines the nature of hardness and cleavage of minerals. Now, the specific gravity is a measure of density of minerals. So in general, metallic minerals tend to have high specific gravity values compared to non-metallic minerals. So there it is, like for example, gold, its specific gravity is pretty high, 4 times the specific gravity of say pyrite, fool's gold. So one way to distinguish gold, true gold from fool's gold is check for its specific gravity, lift those samples feel for the weight, for their weight. The heavier one for its size, if it appears to be heavier compared to its size, that perhaps is gold, right? So there it is. Physical properties help us in recognizing minerals. For example, streak. There is another way to determine if you have a sample of gold or not. Find its streak, powder it. If the powder also has gold on yellow, the color of the gold, what you have is gold actually. If it's fool's gold and powder it, the powder will not have the same color. So physical properties like these help us in identifying minerals. So there it is. Those are some topics that I wanted to talk about and discuss. Do you have any questions? Um, yes, Karina, do you have any question? Can you send me a text? Let's see. I'm trying to. Let's see. Okay, let's see. Oh, oh, I'm sorry. It looks like there were messages. Yeah, it looks like I answered all those questions. Okay, so do you have any questions about these concepts that I discussed? Okay, specific gravity, Yesenia, is a measure of density of minerals. Um, so the density is mass over volume, right? So it tells us something about the packing, the nature of elements present in a particular mineral, and also how packed the atoms and ions are inside that lump of mineral. So metallic minerals have a tendency to increase the specific gravity of minerals, like gold or a sphalerite, which is a zinc mineral, or chalcopyrite, which is a copper mineral. They tend to have, in general, high specific gravity values compared to other non-metallic minerals, like quartz, right? For example, it has lower specific gravity. Now, how are you coming along with the textbook and lab manual purchases? Did you get a chance to purchase them, or you're on your way to purchase them? Any updates there? Sure, that's fine. Okay, that's good. That's good. That's fine. Oh, Subaida, how did you get? Did you get the lab manual also that way? If it is a used one, I need to see, because I don't want them to have any writings on. If it is a used one, not bought from STC bookstore, yes, you can still show it to me. One way is using a webcam if you want to on Blackboard Ultra, or you can bring it to my office. So if it is from STC, then just post the receipt. All right. Tomorrow is not a good time, Yesenia. I have a meeting in the afternoon. Well, let's see. How about on Monday in the afternoon? Are you on time on campus on Monday in the afternoon? I'm in my office in the afternoon, an entire afternoon. Oh, let's see. Okay, all right, Yesenia. I can then go there, go to my office in the afternoon. Now, Subeda, we need to find a way for you to for me to check the lab manual. Maybe Blackboard Collaborate is the way, right? Um, lab material. Let's see. Lab material. Find. See, the first lab is not due until 24th of February. All right. And the lab material, by lab material, Gilbert, what do you mean? Do you mean the books or books and rocks? That's fine, Subeda. When you log on next time, make an appointment. I will log on, and we will come here first. Send me an email. I will set up a session. We'll come here first, and then I'll tell you. Right? We'll go step by step. But send me an email and set up an appointment.